Hello everyone, I'm Norman Wildberger. This is the second video of our famous math problem number 19 problem, which I claim is the most important and fundamental problem in mathematics. And we outlined what it was last time. It's how to model the continuum. And we gave this a difficulty level of somewhere between 4 and 10. Some aspects of it are actually solved. Other aspects of it are very difficult and perhaps insurmountable. Today I want to talk about the rational number line, which we introduced last time in a perhaps novel way geometrically, and then move on to the introduction of irrationalities, which of course goes back to the ancient Greeks and caused all kinds of consternation. Okay, so I claim that this is the most fundamental and important problem in mathematics, and I also claim that the modern idea of real numbers, which most students learn in universities and high schools, is in fact in serious error. Serious logical difficulties with the theory of real numbers, and mathematics is on the cusp of a rather major revolution as we really have to shift focus, shift direction in a major way to get over this hurdle. And it's going to mean a lot of new and interesting mathematics, and we're going to touch upon some of that today. Alright, so obviously this is very contentious, and I'd like to promote the idea of having a reasonable adult discussion about it. And one way to start doing that is to start with a historical view, where we see some of the ideas, how they were developed, how the problems arose, and how famous mathematicians struggled with them. All right. Okay, so there is an elementary solution to this important problem, and it's that the continuum is actually modeled by the rational number line. This is a point of view that really goes back to the very beginnings of mathematics. The Pythagoreans were very keen on rational numbers, natural numbers, tried to express the harmony of the whole world in terms of just numbers and their ratios or proportions. And I introduced last time a perhaps somewhat unusual geometrical way of thinking about the rational number line, which is really more in keeping with the way the ancient Greeks thought about things, except that I have gone in a slightly different direction and not talked about Euclidean geometry, but rather in some more elementary prior geometry called affine geometry. So let me just remind you what the story is there. So in affine geometry, we're working the plane. We only have a straight edge, and we have the ability to draw parallel lines. That's all we're able to do. And so what we can do is we can start off with, say, one line L, which is the main line of interest. Right? We want to sort of establish what we're talking about in terms of points on this line and their relative positions and so on. And to help us do that, we draw a second line M, which meets the first line at some point O. And then let's mark, rather arbitrarily, 2 points, one on L, say E, and another one on M, say F. And with these 3 points, we have then enough to set up the rational number line. And what we do is we first start by drawing parallels to the 2 given lines through these 2 points. So we draw this line parallel to this one, and we draw this one parallel to that one there. So we get another intersection point there, and then we can draw this line here between these 2 points, and then draw parallel to that line through this one, giving us then 2 more intersection points. And we can continue that. So let me just do a few more. So with the new points that we've created, we can create some new parallel lines. So for example there, draw another parallel line. And through this point, another line parallel to these ones. Something like that. And that then gives us more points. For example, these ones. And then we can continue drawing parallels and joining existing points to get more and more lines and more points. And eventually we're going to get a sequence of points marching out along the line, but we're also going to start noticing points in between the ones that we've already created. So for example, we could draw this line here between these 2 points. And then through this point we could draw a parallel to that one that we've just drawn, which amongst other things gives us a new point there, which is going to be for us the midpoint of these 2 points. Right? So in this way we can subdivide intervals and we can create more and more points. And at some point we're going to start noticing that some of the lines that we're drawing and some of the points that we're obtaining can be found in a number of different ways. So for example, this one here could also be found by, say, joining this one with this one to get a point down here, and then joining that point to this one, and then intersecting our baseline with this new line. So we get more and more points, more and more lines, and the framework that we're getting here is the rational number line, but constructed geometrically, not arithmetically. If we were going to impose arithmetic on the situation, well, we would call this 0, and we would probably call this 1. Instead of e, we would call this 2. And then the next one over would be 3. And the one that I've constructed here would be 1/2, and so on. So it's quite an interesting challenge to try to work out the geometry that's required to make this work. But in any case, this is a legitimate framework for the continuum, which in principle is going back to the Pythagoreans, and which really does provide some kind of answer to our fundamental problem. It's a model for the continuum. A natural question that many of you may be asking yourselves is, can we really do mathematics using the rational number line as the continuum? Does it work? It's quite alien to our current way of thinking because most students learn that we need real numbers, we need irrationals, and we need transcendental this and that. Well, the answer is, in my view, a resounding yes. We can build up mathematics, or at least most of mathematics, using the rational number line as the foundational idea of a continuum. But new ideas are certainly needed in order to do that. All right, and some of the new ideas that are going to be involved in this very interesting program are, well, first of all, rational trigonometry, which shows you how to do trigonometry basically only using rational numbers. So that's a key brick in this framework. Then universal geometry, which shows how to use an algebraic framework to extend metrical geometry to Euclidean geometries and hyperbolic and spherical and relativistic geometries and so on. So it's an extension of rational trigonometry to geometry more generally. Algebraic calculus, which I talk a little bit about in my differential geometry series, if you're sort of interested in learning a little bit about that. Going back really to Euler and Lagrange and Newton, okay, this really deserves a renaissance, and I believe that in the coming decades it will enjoy a great amount of reinvigoration. Numerical analysis plays an important role. We start to learn that a lot of the things that we've currently been thinking about in terms of ideal exact elements are more carefully understood in terms of approximations with rational numbers, which is ultimately what the engineers and the physicists are really doing anyway. But so it's an attempt to make mathematics really correspond more to what's really going on out there in the real world of engineering and physics and chemistry and computer science. So numerical analysis, which is usually thought of as an applied math subject, I think it really will play a bigger role in pure mathematics, in framing our understanding. Combinatorics, I think, will play an interesting role, and computer science will be brought into this too, because programs, algorithms are part of how to extend rational ideas further. Okay, there's more things involved here. I'm eventually going to talk about most of these things, I hope, in my Math Foundation series, which is an ongoing work which will probably take some time to unravel. But hopefully in the next century we're going to see more and more people joining the bandwagon, going back to the Pythagoreans, realizing that the rational numbers are the true basis of mathematics and indeed of analysis, and help build this new, more careful, exciting, and beautiful approach to the subject. And maybe some of you can contribute too. Okay, there's going to be a lot of work that's going to need to be done. In the 19th century, this geometrical way of thinking about arithmetic became more clearly understood, but perhaps more in a projective setting rather than the affine setting that I've sketched for you. And I just want to very briefly give you an idea of this projective setting without going into a lot of details. So the way you can think about this is imagining someone who's making these affine constructions on a big, say, playing field, or maybe even a vast plain, long, long lines. And imagine that you're watching them from some distance, and that here is the field on which they're making these constructions, and here's the horizon. Okay? So we're actually witnessing a picture of these affine constructions, but now sort of a real-life picture where there's an actual horizon. So here's our line L, and here's the line M that actually go off, and they would actually end there because that would be the horizon if they actually were produced a long ways. And L would actually end there, but I'm going to sort of show it going further. And here's E and F, our starting points. And now what would the constructions sort of look like? Well, let me just show you how to make essentially the same constructions that I was doing in the affine case, but now where the line at infinity allows us to rethink what parallel means. So in projective geometry, parallel in an affine setting really means that lines meet at this line at infinity. All right. So once we've established what the line at infinity is, then our notion of parallelism means meeting on this horizon. All right, so if we're given this line L and we're given this point F, and we want to create a line through here which is parallel to L in this context, what we have to do is we have to draw a line that goes through the same point here at infinity as L. And similarly, a line that's parallel to this one through E is a line that goes through the same point at infinity. Okay? And that gives us our new point here. All right, so now what did we do? Well, now what we did is we drew some more lines, these diagonal lines. First of all, this one here. Oh. And then through this point, a line that's parallel to this one. What would that mean? Well, I would have to look to see where this line, the green one I've just drawn, meets the horizon. Okay, so it'd be over there some ways. And then we want to draw a new line through this point, which also goes through that intersection point, which is off the page. All right, so let me just roughly make an approximate version of what that might be. Perhaps that's the line there. Giving us then some new points. Say here and here. And then we can create some new lines parallel to the ones that we already have made by, say, through that point, parallel to these lines, would be this one here. And this one here. And I hope you can see that we're having the same kind of construction that we talked about in our the previous video, where we talked about the perspective image of a square. Okay? This is like a picture of a square floor in a perspective view or an artist's view. Right? And we could continue this way, and in that case the points that we would be getting on our original line here representing our rational number line would no longer appear quite so evenly spaced as they did in the previous example. Okay, so this might be 1, that's 0, that's 1, that's 2. Then 3 would be a little bit closer here, and 4 would be closer still, and a half would be somewhere here, I suppose. And so there would be some kind of perspective view of the number line. In addition, what else would be interesting is that now the number line is going to be equipped with a new point. So our numbers are going to sort of start piling up here. Once we get to a million and a trillion and so on, they're going to start piling up towards infinity. And this point right here is actually a new point which we could call infinity. So from the projective point of view, the continuum has a somewhat different nature than it does in the affine point of view, in that there's this extra point called infinity on it. So this is an interesting aspect of the discussion. So does the continuum have a point at infinity or not? Should we adopt an affine point of view, or should we adopt a projective point of view? That's a very interesting question, not so easily resolved. So we maybe have to keep an open mind about the possibility of having different kinds of continuums floating around. Some of them might be more suitable for some kinds of issues or problems, and others for others. And that's a good point of view, that it may be that there's not just one continuum out there. There may be different kinds, and there may be different layers or levels of sophistication. So we'll keep that in mind in our, the spirit of keeping an open mind on this very important question. So this is a projective view of the rational number line, and an interesting exercise for those of you who are geometrically inclined is to sort of try to follow Hilbert and figure out how to define the arithmetical operations, say addition and multiplication, on this line, on this projective, in this projective setting. Very interesting issue. Let's summarize a few important properties of this rational number line that we've laid out so far. And you can think of geometrically along the lines I've described to you today and last time, or you can think more familiarly in terms of just the arithmetic of rational numbers as you were taught in primary school. Okay, so properties of the rational number line. The first one is that it's arbitrarily divisible. Well, that's maybe an awkward sounding phrase. I don't want to say infinitely divisible because I don't like to use that infinite word so much. But what I mean here is that if we have any given segment, we can divide it into n equal pieces, where n is any number at all, any natural number at all. So for example, if this is the interval that we're interested in, so we're thinking of a rational number as being represented by that segment, the way the ancient Greeks did, and we want to divide that into, say, 3 pieces, then this is the construction I showed you last time. We get an auxiliary line, we make 3 copies of equal segments on it, and then we draw a line from this one to that end point there, and then parallel lines to the original one there through these other 2 points. And then these new points that we get here will subdivide the starting interval into 3 equal pieces. And we could just as well have done this with 4 or 5 or 29 different pieces in subdivision. All right, so that means that we can, no matter how small an interval is, and no matter how finely we want to cut it, divide it up, we can do so. Okay? We can do it, of course, arithmetically, but we can also do it geometrically. The second property is that any 2 intervals really have the same geometrical structure. Okay, so here's a way of thinking about that geometrically. Suppose we have 2 different lines, okay, and on this line we have 1 interval, there's 1 interval there, and on another line we have another interval. And this interval looks shorter to us. Maybe we think that there's fewer points on there somehow, or that the structure of points here and the structure of points here should be somehow different. But what I want to show you is that we can easily, geometrically or arithmetically, define a way of corresponding points on one interval to another. So the way we do it geometrically is we join the endpoints here with a line, and we join the endpoints here with a line and see where they meet. And then we're going to think of this as being a perspective point that allows us to connect points from one line to another. So, for example, if at some point we've found by some construction or other a certain point on this line, then by getting our ruler and our perspective point, we just go from our perspective point all the way up there, and we find this point here. So for every point on this interval that we've constructed, there's a corresponding point on this interval that we can also construct just by joining the constructed point with our perspective point. Arithmetically, one way of saying this is that the interval AB, in the usual notation, is in some sense the same as the interval 0, 1. You might say similar. And here's a sort of an explicit formula. If you take a lambda, which is some rational number between 0 and 1, and then you form the combination 1 minus lambda A plus lambda B, that's a convex combination, that's going to be a point inside this interval here. And as lambda ranges through points in 0, 1, this combination is going to range through points in the interval AB. So that's telling you again that arithmetically any interval whatsoever, no matter how big or how small it may be, is in essence the same as, say, the standard interval 0, 1 in terms of the points on it. Right? So even if we subdivide intervals into very, very small intervals, those very tiny intervals that we have still have the same structure in terms of points on them as does, well, the interval that we started with. So there's a kind of a scale invariance to the rational numbers. The rational numbers exhibit a rich layered structure. When we look at an interval or the line, it may look like it's quite uniform. But when we examine it from the point of view of the rational number line framework, we find that it's not uniform at all, or that the uniformity is of a very subtle kind. So that can be illustrated in a number of ways, and here are a couple of videos in the Math Foundations series that exhibit some aspect of that you might want to have a look at for some sort of more deeper aspects of the rational numbers. But I just want to show you a picture of Ford circles, which is one of my favorite aspects of the rational numbers. So these are circles that were discovered by Ford in the 30s. The idea is that if here's our rational number line, and here's some rational number, say, 1/2, then above this point we're going to sit a circle which is just touching the line, whose diameter is, well, if the rational number is p over q, where p and q don't have any common factors, then we're going to create a circle whose diameter is 1 over q squared. So over 1/2 we're going to have a diameter of 1/4. This is 1 here, and so that's supposed to be a diameter of 1/4. So above 0 we get a circle with diameter 1, above 1, above 2, these are all circles of diameter 1. Above 1/2 and 3/2 and 5/2, we're going to get circles of diameter 1/4. But say above 2/3 we get a circle of diameter 1/9. And the beautiful thing is that all these circles don't overlap. They touch sometimes, but they never overlap. Even if we take many, many rational numbers and draw many, many circles, the more rational numbers we draw, the denominators naturally end up getting bigger and the circles get smaller. And there's then a sort of a froth of circles sitting on the number line, increasingly small diameters, that just sit there beautifully. And the way they touch each other is also beautiful and described in say, this lecture here. Okay. So what this exhibits is that far from being uniform, even an interval like 0, 1, actually has a rich layered structure. As we go down, okay, sort of like with a magnifying glass, we are seeing more and more rational numbers with bigger and bigger denominators. It takes more and more work to see the denominators that are big, because they're big and it's hard to write them down. So that's an interesting aspect of the rational number line, and it's also visible geometrically in terms of the number of constructions that you have to make in order to exhibit any particular point on the rational number line. Now, it's something important to keep in mind, that the rational structure is a very subtle one and full of layers and complexity. And the final property is one that played a big role for the ancient Greeks, which is the commensurability between any two rational numbers, or as they would have said, between any two segments. So given any two rational segments on the number line, say A and B, we can find a third segment C so that both A and B are multiples of that smaller segment. So the multiples are natural numbers, like 2 times, 3 times, 4 times, 5 times, and so on. So the way the Greeks thought about that is, here's the number line, and here is a segment, let's call it A. Okay, from here to here is A. And here's another segment, B. And if we're interested in the proportion or the relative sizes or the relative extents of these segments, which was something that the Greeks were very interested in, we can see that this thing is roughly, say, 3 times this one. But if we take 3 copies of this, we see that we don't quite get this thing here. So it's not exactly 3 times this one. So how do we express the relationship between A and B? Well, the idea is to find a smaller segment, in this case C, that has the property that a certain number of multiples of C will exactly be A. It turns out A is 4C. So exactly 4 of these things will make A. And so that another multiple of C will make B. So it turns out that 11 of these C's will make B. So A and B are both expressed as number multiples of some common or some smaller segment C. That's what the Greeks meant by A and B being commensurable. You could measure them both relative to each other from the point of view of some other segment. Now, these days, arithmetically, we would say the same kind of thing this way. If we have two fractions, 2 over 7, say, and 5 over 6, then both of them can be rewritten in such a way as to be multiples of another fraction. And that's actually a very important thing that we do in the arithmetic in primary school. So we write 2 over 7 as 12 over 42. We multiply both sides by 6. And we rewrite 5 over 6 as 35 over 42 because we multiplied both top and bottom by 7. And why do we do that? Because now these two fractions have the same denominators, making it much easier to add or subtract them. So what we're doing here from the Greek point of view, perhaps, is that we're finding this other fraction, 1 over 42, that has the property that both of these are multiples, integer multiples of 1 over 42. In this case, this one happens to be 12 times this one, and this one happens to be 35 times this one. Okay, so that's the arithmetical version. This is the geometrical version that the Greeks thought about. Okay, now we can come to the discussion of irrationalities. Irrationalities first entered mathematics very concretely and explicitly in the time of the ancient Greeks, around the Pythagorean times. That's 500 BC. And with the discovery that when you introduce a circle into the plane, then something happens. You get new points that are no longer in the framework that we got with affine geometry. So the way I'd like you to think about this is thinking about Euclidean geometry as being built up from affine geometry by introducing on top of it the idea of a circle. Okay? Circle is not a notion of affine geometry. So let's say here was our affine plane, and I've created it so that there's a circle sitting here at this point 0. And this circle allows us a notion of perpendicularity, because if we have, say, that line and it meets the circle at that point there, then the tangent to the circle gives us a notion of perpendicularity to the radius. Okay. So once we have notion of perpendicularity, then we can make this axis also perpendicular, and we can use the circle to sort of transfer this segment, which is horizontal here, to the vertical position, which we couldn't do before with affine geometry. Okay. So the circle makes a lot more things possible that are not just possible with affine geometry. In particular, perpendicularity, and in particular, the idea of rotating segments. But it also introduces a very big conundrum that you've all heard about, and that's that this new object, the circle, introduces points which are foreign to us, which don't seem to fit into the pre-existing framework. And we can see that here in a number of ways. One way is to look at the meat of the circle I've just drawn with this line here that goes through that fourth point of this parallelogram. Okay, so this point, let's call it A, it's a point in the plane which cannot be obtained from affine geometry. No amount of drawing parallel lines to existing lines and reiterating many times, no number of ways of doing that will ultimately get exactly that point. You get points which are very close to it, of course, but exactly that point you will not be able to obtain. Another way of saying that is to think about a slightly larger circle. If we take another circle centered here, but going through this point instead, and draw a circle. Let's see what I do. Okay, there's another circle. And meeting the plane, and meeting L now at some new point. So if this happens to be our number 1, and maybe this is our number 2, then this point, let's call it B, is a new point that's no longer one of the many points that we could construct in the rational number line. Okay, and the Greeks realized that this is some kind of number which might be called square root of 2. It has the property that if you square it, so what that means is that if you apply the multiplication property to it, to itself, then you get 2. But that is not a rational number. And you've probably heard the story of what happened to the fellow who exposed this secret. The Pythagoreans were embarrassed about this because they thought that now all of a sudden there are irrational quantities in mathematics and in the universe where they previously had thought that God created just this beautiful thing with only natural numbers. This seemed some kind of imperfection to the natural world. They were very reluctant to acknowledge it and to really deal with it. So this is a very big shadow that still influences mathematics. Okay, you can have a look at my Math Foundations video that I talk about the unfortunate difficulties with square root of 2. So the introduction of circles into Euclidean geometry introduced new points or new segments that the ancient Greeks wanted to use in their geometry, but which they could not fit in to their picture of commensurability with rational numbers. So it was a big headache for them, and but progress was made. So a very brilliant mathematician, Eudoxus, who was one of the great mathematicians of the ancient world, lived around 400 BC, was a student of Plato, developed a geometrical arithmetic with such irrational segments. So even though two segments might not be commensurable, Eudoxus showed how we could still do a kind of arithmetic with these things and still use them in formulas in a very clever, almost kind of modern way. So Nowadays, we recognize that these kind of irrationalities that occur here were really arithmetically due to the idea of introducing solutions to higher degree equations. If we stick to linear equations, the rational numbers are complete. We don't need any more numbers. But if we go to, say, quadratic equations or cubic equations or higher degree equations and we look for solutions, we cannot always find rational solutions. That's the essence of it. So the equation x squared equals 2 is the equation that we get when we try to talk about a circle meeting a certain line. The equation x cubed equals 2 is involved in an important problem called duplication of a cube. This equation here, x times 3 minus 4x all squared equals 3/4, is related to the trisection of an angle problem for 60 degrees. So these are all sort of important problems from the Greek period, and they necessarily involve, as we now know, sort of irrationalities. But what actually are these numbers that we would like to introduce? So we would like to have numbers that solve these equations for us. Of course, that's the most natural thing. But how do we construct such a framework where we actually can legitimately have these objects very clearly defined and that we can do arithmetic effectively with them? Well, that's a big headache, which is still here with us today, and really in some sense that's the essence of the famous math problem 19. Our next development is going to take us up to the modern age, the 17th century, and the introduction of calculus. The introduction of Hindu numerical numbers had a big influence, and a remarkable fellow called Staudt, who really brought the modern idea of our decimal number into wide usage. So we're going to talk about these more modern developments, again with the idea of solving equations, building up a wider notion of the continuum that helps us solve equations. Can we do it? What actually happened? Very interesting issues. And we'll meet a fair number of important mathematicians along the way. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.